after class. Okay. The third exam so covering sections, so it's going to be 3.1 to 3.6 and 4.1 to 4.5. So tentatively we'll have it scheduled for Monday the 26th. Monday, 7/26. So hopefully we'll get to have it then, and in which case we'll have Tuesday and Wednesday as review days, and then the final exam will be on the Thursday there, the 29th. So the final exam on Thursday. And the final exam will cover the whole course, of course. And I'll dig up some like practice exams for you, some old final exams for the course. Okay. So let's get back to section 4.1. This is more on 4.1 and 4.2 together, do both sections together. So exponential functions, and section 4.2, which is on the number E. So yesterday we defined an exponential function. Given a positive real number a, an exponential function with base a has the following form. F of x is equal to k, which is a constant, a, which is a positive constant again, to the x. So the variable x is an exponent. And this number a is called the base. And common bases that are used are 2 and 1/2. Those are common bases that are used in computer science. And then there's this number e that's often used as a base. And e is this special number called Euler's constant. The significance of e, it comes from calculus. And you'll see, why that number is special. But, I mean, it's a real number just like any other. Another common type of base that's used is 10. So 10 is a common one, of course. And then bases that look like this, 1 plus r over 100, where r is some interest rate, like 3% on a mortgage or savings plan or something of that sort. Okay, so examples of exponential functions and evaluating them, like if we had f of x equal to 6 times 1/2 to the x, then f of 3 is 6 times 1/2 to the third, which is 6 over 8, which is 3/4. F of negative 3, which is 6 times 1/2 to the negative 3, which is 8, so you get 48, so on and so forth. An important property of exponential functions is that they are always positive. Never zero, never negative, as long as that k. So the a is always a positive number. You never pick a negative base for an exponential function. So as long as this number k is positive, I mean, it could be negative sometimes depending on the situation, in which case the exponential function is always negative. But it doesn't switch signs. It's never zero, and it never switches from being positive to negative. So if it's positive, it stays positive. And the graph of exponential functions look like that. So y equals ka to the x. For a bigger than 1, the graph looks like this. Right? It has a horizontal asymptote going out to negative infinity, and then it explodes upwards for x is bigger than 0. Right, for negative x's, it goes, it has a horizontal asymptote at the x-axis. It gets closer to 0, in other words, and then it gets really large, really fast for positive x's. If a is less than 1, then it's the same graph, just spun around the y-axis. Okay, so that's basically what exponential functions look like. There's no x-intercept. The y-intercept is at k. And then if you vary the base for different bases, like 2 to the x would look like this, and 3 to the x is just steeper, so to speak. The larger the base, the steeper the exponential function. Exponential functions are classical examples of functions that grow fast. So any quantity that's fast growing often, well, I mean, it has to actually be exponential, but when we discuss fast growing quantities, we often discuss growth that is exponential, right? I mean, I'm sure you've often heard like someone saying that, well, it's growing exponentially or decaying exponentially or something like that. That means very fast, essentially. So the growth of an exponential function that outpaces any polynomial. Eventually. Not necessarily initially, but eventually. Okay. So exponential functions are used for modeling in many situations. Some examples are 1 with compounding interest, 2 with radioactive decay, and 3 often with population growth. So, well, not any population growth, but like unrestricted type population growths, like with bacteria in a petri dish where it's got all the food and space that it wants. Not necessarily like population growth in mammals or rabbits or something like that. So here's a nice example: radioactive decay. So carbon-14 is a radioactive isotope of ordinary carbon. Right, it's got some extra neutrons in the nucleus, which makes it give off, which makes it decay in a radioactive fashion. And one parameter that's often associated with radioactive isotopes of elements is something called half-life. The half-life of carbon-14 is 5,730 years. And that is, what that means is that given an initial sample, given an initial amount A, grams or kilograms or micrograms or milligrams, whatever have you, of C14, after 5,730 years, only 1/2 of A will remain. All right, after another 5,730 years, half of this half will remain. Half of A, which is 1/4 A, will remain. After another 5,730 years, half of this amount will remain. 1/2 of that current amount, which is 1/8 of A, will remain. Right, etc., etc. So it looks like this, right? T in years, amount remaining. So after 0 years, you have A. After 5,730 years, you have half of A. After another 5,730, which is what, 10,000? 11,460. It's 1/2 of 1/2, which is 1/4 A. Or you can think of it as 1/2 squared, or maybe not like that, but maybe like this. After another 5,730 years, which is 17,190, it's 1/2 to the third A. After another, so it's 22,920. So on and so forth like that. Okay, now the rate of decay is continuous. In other words, you don't have to measure in intervals of 5,730 years, right? So a continuous, unbroken function whose amounts, do equal this every 5,730 years would look like this. Therefore, the amount of C14 remaining from an initial sample A of therefore a function that measures the amount which measures the amount of C14 remaining from an initial sample A after T years, not necessarily in intervals of 5,730, is A of T, we'll call it, and that's going to be A times, so maybe I shouldn't use A here, let's just say F of T, equal to A times 1/2 to the T divided by 5,730 years. So when T is a multiple of 5,730, this right here is going to be an integer. So for T equal to 5,730, it's 1, so you get a half. For double 5,730, you get 2, so you get 1/2 squared. For triple 5,730, this exponent is 3. So at every 5,730 years, this function matches what's in the chart here. Okay, but you don't have to, have T in some multiple of 5,730. So, for example, the amount, so suppose we have an initial amount of 10 milligrams of C14. How much remains of the C14 after 10,000 years? Right, so that's going to be, starting with the function, 10 milligrams times 1/2 to the T divided by 5,730. Okay, well, after 10,000 years, we have 10 times 1/2 to the 10,000 over 5,730. So that's nearly 2 cycles of the half-life. So you would expect about 1/4 of the 10. So about 2.5 milligrams, a little bit more, because it's not exactly 2 clicks of 5,730 years, right? That would be 11,460, but it's pretty close, right? So maybe like 3. We expect the answer to be maybe around 3. So let's check it out. So how do you deal with exponential functions on your calculator if you have not done so already? So here is something that may look like the calculator you have. There's that. What else? I think I have another one here. Maybe that one is more like a graphing. Yeah, this one is kind of more like a graphing calculator, I think. I think this button is maybe more, yeah. All right. So on your calculator, so you're going to have like various buttons on your calculator. The one for dealing with exponential functions is right here. See that? It says x to the y, or it may say a to the b, or x to the n, or something like that. Right? So this button x to the y is for using exponential functions. There's also, you should have a button on there for e somewhere. Right? So here's my button for e. Right, and there's that number. It's 2.7182, blah, 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 blah. It's like pi. It goes on infinitely with no repeating pattern. So when we get to using this base here, and I'll have I'll have some example for that in a moment, but here's that button there. But here's the button for exponential functions. So how does this work? Right, 2 to what power? Let's say 2 to the 4th. Right, so first we do 2, and then we click this thing, exponent 4th. So 2 to the 4th, well, we know that's 16, and there it is. And so it shows it right here. So 2 to the 4th is 16. Right? Or 2 to the 5th, right? That's 32. Right? 2 exponent to the 5th. And, right, if you want to do exponents on the computer screen, or in a browser or on Wolfram Alpha, the symbol that's used for exponent is this thing here, this little caret mark, and that's above the 6 usually on your keyboard. All right, we're using that. So you can just use the search bar on Google, for example, or on Chrome or whatnot. So 2 to the 10th, for example. So this character here is above the 6. So 2 to the 10th, push that, and Chrome has a calculator built in, 1024. You can also go to Wolfram Alpha and do exponents there, 2 to the 10th, and it gives you the answer right away, actually. 1024, or you can do it like this. All right, so here, so sometimes these things are a little awkward to do on your calculator. Okay, sometimes they're a little awkward to do on the calculator. It might be more convenient to do it on a browser, but if you want to do it on your calculator, this is how it goes. So we're calculating this right here. 10 times 1/2 to the 10,000 over 5,730. Okay, so first we'll start with the 1/2. So 1/2, 0.5. Right? To the exponent. Now, this exponent, it's a quotient. 10,000 divided by 5,730. So I got to use these parentheses here. Okay, so left parentheses, 10,000 divided by 5,730, close parentheses. Now, you should have a window on there on your calculator. If you've got one of those graphing calculators, it'll have that window for you. Right, so it shows me that I've got the right thing. 1/2 to the 10,000 divided by 5,730. And that's equal to this, 0.298. And of course, I need to multiply that whole amount by 10. So right about 3, right? 2.98, 2.98 milligrams. Just like we were saying, it was almost, 2 cycles of the half-life. So 5,730 times 2 is 11,460. So for 10,000 years, we should divide the initial amount of 10 by something close to 4, not quite 4. So when you divide 10 by 4, you get 2.5, right? So it should be a little more than that. And we were saying maybe about 3, and it was a pretty good guess, right? 2.98 milligram. All right, so those are half-life examples, and carbon-14 is one of the elements that's used for what's called radioactive dating or radioisotope dating of things. Although it's only accurate for there's problems in using it, and it's only accurate for, I don't know, something like 10, 20,000 years or something. Its accuracy doesn't go beyond that. But there are other types of radioisotope dating, in particular uranium-lead dating, which is much more accurate but is used for much larger time periods. And those get talked about a lot in sort of popular articles. Another place for exponential functions is with compounding interest. So a simple example of compounding interest is something like this. So supposing that a savings account at a bank pays its investor an interest rate of 2% compounded, and you're going to have so many compounding periods. So 2% compounded yearly, compounded quarterly, compounded monthly. Usually it's monthly. Compounded monthly, compounded daily. So many compounding periods per year. So let's say compounded monthly. That is 12 times a year. In roughly equal time spans. 12 times per year in roughly equal time spans. In which case, so if you have an initial investment of $A in such an account, then the amount of the investment f of t after, say, t years would be the following. So f of t is equal to, so you have this initial amount, and then it gets multiplied by this formula here. So 2%, okay, that's 0.02, like that. So 2% as a number, you have to divide it by 100. So instead of putting 2 over 100, let's put 0.02. And because it's compounded monthly, what that means is that 2% is divided by 12, and it comes, some smaller number. But that interest is paid 12 times per year. So 12t, like this. So the amount of the investment after, t years, it looks like that. Right? So 1 plus 0.02 over 12 times 12t. If you're only compounding once per year, then it looks like this. Once per year, then it looks like this. F of t is a times 1.02 to the 12, or sorry, to the t. So 0.02 divided by 1 to the 12t. If you're compounding 4 times per year, in other words, quarterly, you would say, it would look like this. F of t is a times 1.1 plus 0.02 divided by 4 to the 4t. Right? So interest is paid out 4 times a year, but not 2% 4 times a year, 2% divided by 4. Right? Here, interest is paid out 12 times per year. right? But not 2% 12 times, 2% divided by 12. Here it's only paid out once a year. And, it could be compounded daily. Then it looks like this. F of t is a times 1 plus 0.02 over 365 times 365 t, not counting leap years. Okay, so let's take an example of that. So say an initial amount of $5,000 is invested at 3% compounded monthly. How much is the investment worth after 5 years? Not that you would ever see anything at 3%. Any savings account, or I don't know, maybe like a 10-year CD. You might find it at 3% these days. I don't think so. I think 2% is about the max you'll ever see. Nobody, I don't know who actually uses these things anymore. So the function that goes along with this is f of t equals 5,000, 1 plus 0.03 over 12 to the 12t. So now we're going to, so let's work out what this base here is supposed to be. So this is equal to 5,000 times, so 0.03 divided by 12, 0.0025. Okay, so 5,000 times 1.0025 to the 12t. So how much is that worth after 5 years? So after 5 years, we have f of 5 equal to 5,000 times 1.0025 to the 12t. And that's going to be equal to, so let's look at this on the calculator again. Okay, I've got 1.0025, 1.0025. And here's that exponent button, right, to the, 12t. 12t is 5. 12 times 5, of course, is 60. So 1.0025 to the 60 is equal to this number, 1.161616, times 5,000 equals, right, $5,808.08. And what was it? 8 cents. Suppose we were compounding more. Suppose we were compounding daily. How much would the same investment be worth after 5 years? Right? Does it make a difference how many times you compound per year? Absolutely it does. The more compounding periods you get, the more sort of growth power the same interest rate has. although it's not that big an increase. So let's check it out. So if you were compounding daily, you would use this function. So 5,000 times 1 plus 0.03 divided by 365 to the 365t. So that's 5,000, and let's see what this base here is supposed to be. So 0.03 divided by 365. So 1.00. So let me show you on the calculator. This is a so 0.03 divided by 365. Right. So 8. Remember this notation. Right. 8.2191 to the negative fifth, to the exponent negative fifth. Now, unfortunately, this e doesn't mean the e Euler's constant. It just means 10 to the negative fifth. So this is 4 zeros with an 8 at the fifth decimal point. Right, so move the decimal point from here 5 spaces to the left. All right, so 1, 2, 3, 4, 5. So 8,21917 000812197. No, I got that wrong. 8,21917 to the 365t. You know, you might not want to truncate that like I just did. Maybe just use this same calculation every time. But, you know, we'll just go with this for now. So after 5 years, your $5,000 investment is equal to 21917 to the 365 times 5. So, you know, again, it is a little bit awkward sometimes to do these calculations on a calculator. But let me show you how this goes. So it's 1.12348211917. All right, that's the base, to the exponent 365 times 5. So we have to use these parentheses for calculating the 365 times 5. So this is equal to 1.16182, and that gets multiplied the whole thing by 5,000. So what do we get? 5,809 and 13 cents. So a little bit, a gain of $1. So with more compounding periods, you get more growth. The difference between monthly compounding and daily compounding is really not that much, but the difference between compounding once a year as opposed to compounding monthly, that is, you know, a somewhat significant difference. But the more you compound, the more compounding periods you have, the more growth there is in such an investment. So, you know, I mean, if you were compounding daily, that's a lot. What if you were compounding hourly? Or what if you were compounding every minute, or compounding every second? Again, more compounding gives you more growth, but the growth is not that much. But what's the upper limit? There is an upper limit. Called continuous compounding. So given an initial investment A of $8. Okay, invested at R%, compounded continuously. So compounded continuously, so it's always compounding. Or like think about it as like compounding every second or something like that. What's the formula for dealing with that? Do you have to use this one? Well, interestingly enough, this is the first time that that number E shows up. The amount the investment is worth after T years is F of T equal to A E to the interest rate R times T. Let me make sure of that. Or 1 plus R, or is it to the RT, or 1 plus R times T? No, E to the RT. Well, I'll find out in a moment. So, for example, after 5 years at 3% compounded continuously, $5,000 is worth F of 5 is equal to 10,000, and then you have E to the 0.03 T, like that. So 3%, you have to write it as, as a decimal, 0.03. Okay, so let's check that out. So here's this number E right here. On some calculators, it'll say EXP. The E might be that. But here, so let me clear all this out. E to the exponent 0.03 or times 5. Should be a 5 here. 0.03 times 5. 0.03 times 5, close the parentheses. So this is the E right here to the exponent 0.03 times 5 equals that. The whole thing times 5,000 equals $5,809.17. So compare that to the answers from before. So compounded monthly, 5,808.8 and 8 cents. $5,809.13. So that was compounded monthly. Compounded daily gave you a little bit of a kick, but not that much. And more compounding periods give you a little bit more of a kick until you get to like continuous compounding, and that's the upper limit right there. But it's a little bit more. I mean, here we got 4 cents extra, right? 13 cents, 17 cents. If you were only and this is in contrast to compounding once per year. So compare all of these to compounding once per year. So then F of 5 would be equal to 10,000. or not 10,000, it was 5,000, wasn't it? 5,000 times 1.03 to the 5. So 1.03 to the exponent 5 is this times 5,000. So 5,796 and 37 cents, was it? Yeah. Right, so compounding once per year, 5,796. Compounding 12 times per year, right? So that gave a jump of $10, 5,808, 5,809 and 13 cents. That's for compounding daily, and then compounding continuously, which is the upper limit of what compounding periods gives you, 5,809. But I mean, there's somewhat of a difference between here and here. So I mean, if you're talking about larger and larger amounts of money, it can make a difference. So those are two really common situations for exponential functions. What about some other ones? Let's see. Oh yeah, this is an interesting one. Number 26 in section 4.2. This is not just purely an exponential function, but it's a function that uses an exponential quantity within it. And this is called a logistic function. So, I mean, they've got all these words that go along with the problem. It says a 50-gallon barrel is filled completely with pure water. So you've got some barrel, 50 gallons. So 50 gallons of water. So pure water to start. And then salty water is pumped into the tank. So salty water containing 0.3 pounds per gallon of salt is pumped into the tank. At a rate of, oh, it doesn't even say that. Is pumped into the tank. It doesn't say at what rate. This is a classical type of problem that you'll do in later courses, but they're just sort of getting you used to the idea of it. So the salty water is pumped into the tank, and the salty water has 0.3 pounds per gallon of salt dissolved into it, is pumped into the tank while the rest is drained out. Right, so you've got your big old gallon, and it's got 50 gallons of salty water in it. 50-gallon capacity, right? And you have salty water being pumped in, and whatever's in the tank is being drained out at a similar rate, so that you always have 50 gallons in the tank, right? So this has got 0.03 pounds per gallon of salt. So what happens over time here? So as time progresses, what happens to the water in the tank? How salty should it be? Right? Over time, the concentration of salt in the tank should approach 0.3, not 0.03, 0.3 pounds per gallon of salt dissolved in it, but never completely that, right? It should approach that amount, but never be completely that. It starts out with 0 pounds of salt per gallon, and it should start approaching 0.3 pounds of salt per gallon. The quantity of salt in the tank in pounds at time t, so what is it in this problem? Minutes? I don't even say. Yeah, minutes. Is given by the following, what's called logistic function. And it looks like this. Q of t is equal to 15 times 1 minus, and here's the exponential bit, e to the minus 0.04 t, like that. 15 times 1 minus e to the 0.04 t. And the graph of this function looks like this. So here's t, and here's q of t, and here is 15. And 15 turns out to be a horizontal asymptote, and the graph of the function looks like that. All right, so this is y equals q of t. And that's called a logistic growth function. You could also have a logistic decay function, which goes like that to a horizontal asymptote like this. But this one is a logistic growth because it's an increasing function. Right, so for example, in part A, how much salt is there after 5 minutes? Well, that would be q of 5. So it's 15 times 1 minus e to the minus 0.04 times 5. Okay, so let's see how to plug that into the calculator. So start with this exponential part right there. So that's the comp. So again, it's always a little awkward, I think, using the calculator to do these because you don't go from left to right. You kind of have to start at this part here. So E. So you should have some button for E somewhere. E to the exponent, and it's going to be 5 times negative 0.04. So 0.04, and then you should have a positive negative button somewhere. All right, so it keeps flipping the sign like that. 0.04 times 5 minutes. Right, so here it is. E to the 0.04 times 5 negative equals that, and we're going to subtract that from 1 minus 1. And we get this, which is a negative number, but it should have been 1 minus that, so we just flip it to be positive. So 0.1812. Something went wrong. Subtracting from 1. then times 15. Oh no, that's right. Times 15 gives us, I've lost track of what I'm doing here. Let's try it again. E to the exponent, 0.04 times 5, make that negative there, equals this amount here, make it negative, add it to 1, and you get that amount times 15. So 2.719 pounds. Of salt. How much salt is there after 10 minutes? Well, that would be Q of 10, which is 15 times 1 minus e to the negative 0.04 times 10, which is going to be equal to e to the exponent negative 0.04 times 10, so equals this much, 0.67. Make that negative, add it to 1, and 0.329 times 15. So 4.94 pounds of salt. But, in part C, they ask you to draw the graph, and it looks like this. And as I was saying, after so much time, it should approach 15 pounds, but not after 10 minutes, apparently. 10 minutes isn't quite enough. Let's see, how about 100 minutes? After 2 hours. So that would be Q of 120 minutes, which is 15 times 1 minus e to the negative 0.04 times 120, which is going to be so e to the 0.04 negative times 120 equals that negated, add 1, times 15. So this one should be closer. So, yeah, 14.999. Right, so approaching that 15 pounds of salt in the tank, which would be exactly 0.3 pounds of salt per gallon, right? 0.3 times 50, 0.3 times 50, so that's 50 times 3 is 150. Bring the decimal place over there. So 15 pounds total would be the amount of salt in this concentration per gallon. So that's what this kind of function, this type of situation would look like, this type of mixing problem. Gives you this logistic growth function. There's other situations in which you have, mixing problems with this type of logistic growth. This is just sort of the classical example. And you'll go over this classical example in Calc 2 and in differential equations. I mean, if you go on that far to these other mathematics courses, it's a nice example, these mixing functions, but they come in a lot more varieties than just this saltwater problem. Okay. All right, so that's all the material in sections 4.1 and 4.2. I'll post some homework problems for these sections, and I'll send that to you with the email after class. And other than that, I'll see you tomorrow, okay? All right, have a good day, everyone.